Welcome to the video lecture for course code U18Esit404, course name Digital System Design. And I am Dr.B.Dhanalakshmi, Professor, Department of Information Technology, Bharat Institute of Higher Education and Research. And in today's lecture, we are going to see Unit 1 topic Review of Number Systems. So first we will see about digital computer systems. Digital systems consider discrete amounts of data. For example, in alphabets, we have 26 letters and basic decimal digits are 10 digits from 0 to 9. And large quantities can be built from discrete values, like we can make words out of letters and numbers made of decimal digits. And computers will always operate on binary values which are 0 and 1. And it is easy to represent binary values electrically. For example, voltages and currents, and even while implementing in the circuits and create the building blocks of modern computers, we use digital computer systems. And now we are going to see what are number systems. Number systems are the technique to represent the numbers in the computer system architecture, like every value that you are saving or getting into or from the computer, and they are defined as a number system. So we use number system in our real world life. So number systems are, we have a number of number systems here listed as binary, where it uses digits 0 and 1 with base 2, and octal which use digits 0 to 7 with base 8, and decimal number system which uses 0 to 9 with base 10, and hexadecimal number system with digits 0 to 9, alphabets A to F with base 16. And now first we will see about decimal number system. So decimal numbers are made up of decimal digits which ranges from 0, 1, 2, 3 up to 9. And decimal number can be represented as, so an example is given how to represent like decimal representation of the number 8653. So that can be represented as 8 into 10 power cube plus 6 into 10 power 2 plus 5 into 10 power 1 plus 3 into 10 power 0. So we start assigning power 0 from the least significant bit. Since the base for decimal number is 10, since we have the numbers from 0 to 9, totally 10 numbers in decimal digits, so we have the base for decimal number system as 10. So decimal fraction is represented as like before decimal point. So that can be represented with positive power, and after decimal point can be represented with negative power. So here 97,654.35. So before decimal, it can be represented as 9 into 10 power 4 plus 7 into 10 power 3 plus 6 into 10 power 2 plus 5 into 10 power 1 plus 4 into 10 power 0. And the decimal, after decimal, the digits are represented with negative power, so which can be represented as 3 into 10 power minus 1 plus 5 into 10 power minus 2. An informal decimal notation we can represent as 97,654.35 to the base 10. And we use 10 digits as base for decimal numbers. Sorry, we use 10 as the base for decimal numbers. And understanding octal numbers now. So octal numbers are made up of octal digits, which are 0, 1, 2, 3, 4, 5, 6, and 7. So octal number can be represented as, say, 44,536 can be represented in octal form as 4 into 10, 8 power 3 plus 5 into 8 power 2 plus 3 into 8 power 1 plus 6 into 8 power 0. So here for octal numbers, the base is 8. So we start assigning the position from the least significant bit with power 0. So here in the decimal, we can represent this as 1362, which will be seen in the lecture later. So octal fraction can also be represented as 465.27. The octal number can be represented as, now before decimal point, 465 is represented here as 4 into 8 square plus 6 into 8 power 1 plus 5 into 8 power 0 plus 2 into 8 power minus 1 for the decimal value. After decimal, the number 2 is represented with negative power. So 2 into 8 power minus 1 plus 7 into 8 power minus 2. And octal numbers don't use the digits greater than 7. That is 8 or 9 is not allowed, or more than that is not allowed. It allows only the digits from 0 to 7. And now we will see about binary numbers. So binary numbers are made of binary digits, that is bits, 0 and 1. So binary number is represented as 1011 of binary form. We get this with a base 2. Binary number has the base 2. So from the least significant bit, it starts with power 0 and so on. So the least significant bit 1 is multiplied by 2 power 0 plus 1 into 2 power 1 plus 0 into 2 power 2 plus 1 into 2 cube. And in decimal representation, 11 is the decimal value for the given binary number. So this conversion we will be seeing in the next few slides. Binary fraction can be represented as 110.10. That is, after decimal, it will be represented with negative power. So after decimal, we have 1 and 0. So 1 will be multiplied by 2 power minus 1 plus 0 will be multiplied by 2 power minus 2. And before decimal, the least significant bit is represented as 0 into 2 power 0 plus 1 into 2 power 1, and the most significant bit 1 into 2 power 2. And the group of 8 bits of binary numbers are called as a byte. And group of 4 bits of binary number is called as a nibble. And now we will see why we use binary numbers. So computers use the binary number system to manipulate and store all of their data, including numbers, words, videos, graphics, and music. So it is very easy to represent 0 and 1 using electrical values. So here it is, this binary number system is possible to tolerate noise, and we can easily transmit the data since the machines can understand the binary language, that is zeros and ones, and it is easy to build binary circuits. And now this table shows the growth of binary numbers. Say n, number n, that is 0, the first number, can be represented as 2 power 0. If 2 power 0 is there, the corresponding binary value will be 1. And if it is 2 power 1, then the decimal corresponding value is 2. So 2 power 2, 4, 2 power 3, 8, and so on. That is 2 power 5, 2 power 6, up to 2 power 40, which is represented as tera. And 2 power 30, that is 1 gigabyte. And then 2 power 20 is 1 megabyte. And next we will see about hexadecimal numbers. The hexadecimal number system often is called as hex. Is a numeral system made up of hexadecimal, uses the decimal numbers and 6 extra symbols, that is 16 symbols in total with the base 16. So hexa digit can be the 16 digits starting from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, followed by A, capital letter A, B, C, D, E, and F. So in total, the hexadecimal number system has 16 digits. And each hexa digit reflects a 4-bit binary sequence. The prefix 0x is used in code to indicate that the number is being written in the hexadecimal. If a number is given and if it starts with 0x, we can say that it is an hexadecimal number. So hexadecimal number can be represented as, for example, 4536 in hexadecimal can be, that is, it can be represented as least significant bit 6 into 16 power 0 followed by plus 3 into 16 power 1 plus 5 into 16 power 2 plus 4 into 16 cube. So the most significant bit here has the power 3. And the decimal hexadecimal representation, fractional representation can be done after decimal point. We can use the negative power. So after decimal here we have number 2. So 2 into 16 power minus 1 plus 7 into 16 power minus 2. And before decimal 5 into 16 power 0 plus 6 into 16 power 1 and the most significant bit 4 into 16 square. And now we bring all the number system in a table. Here the first column represents the decimal number system and the second column represents the binary number system and the third column represents the corresponding octal number system and the last column represents the corresponding hexadecimal number system. So here from 0 to 15 the numbers have been given in decimal. So the corresponding binary value for 0 to 15 is given in the second column. And the octal numbers here 8 and 9 are not allowed. So 0 to 7 and then the corresponding octal converted values have been given in the table third column. And finally hexadecimal where we have 16 digits starting from 0, 1, 2, 3 etc. up to 9 followed by capital letter A, B, C, D, E and F. So here binary, octal and hexadecimal more or less looking similar and it is very easy to build circuits to operate on these number representations. And it is possible to convert between from any number system to another number system. So conversion between number bases. So decimal can be converted to binary and binary can be converted to decimal and we can even convert binary to octal, octal to binary and binary to hexadecimal and hexadecimal to binary. So between bases we can convert and hexadecimal is described here in the next slide. Hexadecimal to decimal, decimal to another base. Okay, so first we will begin this conversion from decimal to another base, like any base you want. Okay, so first for each digit position, we have to divide the decimal number by the base 2. If you are going to convert to binary, you have to divide that by base 2. So here when you divide, the remainder is the lowest order digit. So here the quotient value of the division result is stored as A0, A1, A2, A3 and the remainder values are stored in the second column here. And when the number 13 is given, which is in decimal, we need to convert this into binary value. So we start dividing this decimal value by 2. So when you divide 13 by 2, we get 6 as the quotient. So here the remainder is 0.5, right? Half. So that has been stored here. And again, the quotient value is taken here and we divide again 6 by 2. So when we divide here, we get 3 as the quotient and remainder as 0. So here the A1 value is 0. If you have the remainder, we represent the A value, the coefficient value as 1. If the remainder is 0, we reflect the coefficient value as 0. So next quotient is 3. So again we divide that by 2. So when you divide 3 by 2, the quotient is 1. And again here we have remainder. So this A2 will be 1 now. Again we take this 0.5 here, that is 1. 1 in the sense the coefficient 1 divided by 2. And here the quotient is 0 and we get the remainder as 1. So here A3 will also reflect 1. So here we repeat the first two steps until no divisor remains, until no quotient. Quotient is 0 is the stopping condition. So now you are going to consider from the most significant bit in the coefficient value and give your output in the binary form. So the most significant value here in the coefficient is A3. So A3 value is 1, followed by A2 value 1, followed by A1 value 0, and followed by A0 value which is 1. So 13 decimal representation can be converted as 1101 in binary form. And now we will see how to convert a fraction from decimal to another base. So for each digit position, multiply the given decimal number by the base 2 for binary number. So the integer is the highest order digit. And we have to repeat the first two steps until the fraction value becomes 0. So now the value, decimal fraction value given here is 0.625 in the example. So 0.625 first multiplied by 2 and we get 1 plus the fractional value you are separating as 0.25, and again the 0.25 we are considering for the next cycle. So this 0.25 into 2 we get 0.50 and the value here is 0 here, the coefficient value. So this a power minus, that is here we have the power 0, sorry, power negative power for the decimal fractions. So a power minus 1 is 1, a power minus 2 is 0, and next we are multiplying 0.5 by 2 and we get 0 as the value, 1.0 as the value. So here 1 is considered as a power minus 3. So now we are going to write from the most significant bit which starts with 101. So since it is decimal, we are writing it as 0.101. And now we will convert an integer from decimal to octal. So a number is given here in decimal form and we are going to convert that into octal form. So when you want to convert into octal form of base 8, we have to divide the given decimal number by 8. If in case if the given decimal number has to be converted to binary, you have to divide the given decimal number by 2. If it is hexadecimal, we have to divide this decimal number by 16. So here we have to divide the decimal number by the destination number format or a base. Clear? So the base value of the destination number to which you are going to convert, that should be given as the denominator value here. So here 175 is divided by 8 and where you get the quotient as 21, and here we just represent A0 as 7 now as the coefficient value, and next 21 quotient value is taken 21 divided by 8. So here the quotient here is 2 and coefficient value here is 5. So followed by the 2, the quotient 2 is divided by 8 where the quotient is 0. So here the A2 coefficient value is given as 2. And now we have to take from the most significant bit, that is from A2 which is 2 followed by A1 which is 5 followed by A0 which is 7. So the corresponding octal representation for 175 in decimal form is 257 in octal form. And now we will see the conversion from fraction value from decimal to octal. So a fractional value is given 0.3125 in base 10 decimal number. So that has to be multiplied by octal, that is octal base, which is 8. So since we need to convert into octal, we are multiplying here, since it is a fractional value, we are multiplying by the base of the destination number format system. So here 0.3125 into 8. So where you get the before decimal point as 2 mantissa part, and the fractional part here is separated as 5. So here the a power minus 1 is 2 in the coefficient. And again now 0.5 is multiplied by 8. So here we get 4.0, where the fractional value is separated and the mantissa value is separated. So that 4 is stored in a power minus 2. So we take from the most significant bit, which is a power minus 2, followed by a power minus 1. So that is 0.3125 in decimal form can be converted to octal form as 0.24. And now we will see the conversion technique between base 16 and base 2. So here the conversion method is very easy, like determine the 4-bit value. Separate the given hexadecimal in 4-bit value. So determine 4-bit value for each hexadigit, and note that there are 2 power 4 is equal to 16 different values of 4 bits. Easier to read and write in hexadecimal, and here the representations are equivalent to the other number systems. So here the example given is 3A9F to the base 16, which is an hexadecimal. Now we represent 3 as 4-digit representation of binary as 0011, and A can be represented as 1010, and 9 can be represented as 1001, and F can be represented as 1111. So the whole hexadecimal converted value of the given binary value for the given hexadecimal is 0011, 1010, 1001 and 1111. So this will be the corresponding binary value for the given hexadecimal number 3A9F. And now we will see how to convert from base 16 to base 8. So here we just club the numbers with 3 digits. From the least significant bit, we start allocating. So 3 bits together, we are going to join. So from the least significant bit, we are going to join 111 first, followed by 110, which is identified as 3, and followed by 010, which is identified as 2, and 101, which is identified as 5, and 011, which is identified as 3. So we are converting from base 16 to base 2. So here the regroup bits into groups of 3 starting from right. So here we ignore the leading zeros, and each group of 3 digits forms an octal digit. So now we will see how to represent signed numbers. So plus and minus sign can be used for representing the numbers. So for computers, desirable to represent everything in the form of bits. So we have 3 types of signed binary number representation, namely signed magnitude, 1's complement and 2's complement. So in each case, leftmost bit indicates sign, that is positive or negative. So positive is represented as bit 0 and negative is represented as bit 1. So we consider the sign magnitude as, so for example, in the given example, it is 00001100. So here in this 8-bit, the first bit is considered as a sign bit always, followed by the magnitude. And the second example given, it is 10001100. And here 1 represents that it is the negative number of the, like since 1 is present, we are saying that it is the negative number. And how to find 1's complement representation? The 1's complement of a binary number involves inverting all the bits. So 1's complement of 0011 is just inverse the numbers. So zeros are converted to 1 and ones are converted to 0. And there is another example where one's complement of the given number is just reverse the number 1 as 0 and 0 as 1 in the output. So here the ones complement of 1010 is 010 10010. So for an n bit number n, the ones complement is 2 power n minus 1 minus n. So it is called diminished radix complement by Manu since ones complement for base radix 2. To find negative ones complement number, take the ones complement first. How to take the ones complement? We have to reverse zeros to 1 and 1 to 0. So here the given example 00001100 can be represented as ones complement as 11110011. So that will be the binary form, and if 1 is present in the sign magnitude, then it is called negative number. Then it represents here minus 12 with a base 10. And if the least significant, that is most significant bit, that is the sign bit is 0, then it denotes it is a positive number. And how to find 2's complement representation? So here we invert all the bits first, like 1's complement, and then add 1. So here 2's complement of 00110011 is convert first this into 1's complement. That is 11001100. And you have to add 1 to it. So that will be your 2's complement value. For an n bit number n, the 2's complement is 2 power n minus 1 minus n plus 1. So here it called the radix complement by Manu since 2's complement for base with radix 2. And to find negative of 2's complement number, take the 2's complement. So here negative number can be replaced by finding the 2's complement of the given number. So here the given number is 00001100, and here the 2's complement number is 11100100. And finite number representation. So missions that use 2's complement arithmetic can represent integers in the range minus 2 power n minus 1, which is less than or equal to n, and which in turn less than or equal to 2 power n minus 1 minus 1. So it ranges from negative to positive. So where n is the number of bits available for representing the number n. And note that 2 power n minus 1 minus 1 will be will be equal to 011 to 11. And in the same way, minus 2 power n minus 1 can also be represented. And for 2's complement, more negative numbers are there than positive. So for 1's complement, 2 representations for 0. For an n-bit number in base with radix z, there are z power n, which are different unsigned values. And it can range from 0 to z power n minus 1. So how to do 1's complement addition? So first we have to find the 1's complement. So 1's complement, using 1's complement numbers, we can add the numbers very easily. Suppose if we want to add 1100 in binary form and 0001 in binary form. So how to add this? Since if you feel that the given number, example or positive numbers, then the sign bit will be 0. And if it is negative, then the sign bit will be 1. So here 12 with the base 10 can be represented as 1100, whereas 01100 will be the representation in 1's complement. And when you try to add the given numbers, so when we try to add the given numbers, so we get 0 plus 1, 1, 0, 0, 0, 1, 0, 1, and 1, 0, 1. So now again we are adding 0, and finally we are getting 0, 1, 1, 0, 1. And binary addition. What about binary addition normally? So we have 1, 1 as 0 with carry 1 and 0, 1 as 1 with carry 1 again. So 0 will come in the denominator and next you will have 1 as the carry. So all three ones we have to add. So again we are getting 1 carry 1. So here 1, 1, 0 with carry 1. So here we get 1 again with carry 1 and here we are getting 0 with carry 1. So in total we are getting the value, the addition result as 1010100. And binary subtraction, we can also perform subtraction with borrows in place of carries. Let's subtract 10111 from 1001101. So here we are going to borrow, right? If the numerator is 0. So here 1 minus 1 will be 0, the least significant bit. And when you subtract 1 from 0, we get 1 again, we borrow 1. And again now, since we have borrowed, now the third position result will be 1 here. And the fourth position here will be 0 minus 0, 0. And again, fifth position here, the numerator is less. So we are borrowing again. So again, we get 1 as the output. And again, since we borrowed here, so here we get 1 and then the result output of this bit will be 1 and at last it will be 0. And binary multiplication is much the same as decimal multiplication. Like first we multiply the least significant bit of the second multiplier with the least significant bit of the first multiplier. So 0 is multiplied with 10111. So that will be your first level. Second level, 1 will be multiplied by 10111. And then again 0 will be multiplied by 10111. And at last 1 will be multiplied by 10111. Clear? And we have to add the numbers at the last. And how to do ones complement subtraction? So first the 12, the decimal number here is represented in the binary form, and here in ones complement we have to take the ones complement of the second operand. So here we are going to subtract 12 minus 1. So 1 is the second operand. So we have to take ones complement of the second operand and then add like a normal binary addition. So here is an example where the second operand is considered as ones complement. So ones complement of 1 is 11110. So now we are going to do the normal binary addition. And 2's complement addition, we are adding the binary numbers and we are ignoring the carry bit. So what we have to do is we have to use the 2's complement numbers, and here we supposed to wish here 12 and 1. So 12 is represented as 1100 and 1 is represented as 0001. So here in 2's complement the first operand is represented 1100 here, and here it is represented, the second operand is also represented, and finally we are adding the number with normal addition. So while adding, we have to find the 2's complement of second operand. So second operand or 2's complement has to be considered for the second operand and then finally add. Thank you.